I hope you've taken the time off there to get yourself a cup of coffee, a nice cup of tea, maybe a soft drink, a glass of water, or something else. And now you're back and ready to hear from Jerome Henry about the importance of rate switching and what it's really all about. So, we heard somebody say earlier today, if you'll remember on our panel, that it was one of those moments of enlightenment that they had while studying Wi Fi. So, here's your opportunity with Jerome Henry.
Hello, everyone, and welcome to this session on rate adaptation algorithms. My name is Jerome Henry. I'm a principal engineer at Cisco Systems and CWNE 45. In this section, I wanted to go a little bit beyond the 802.11 standard itself to look into the engineering of what happens inside your device when it chooses a data rate or an MCS modulation encoding scheme. This is a question that I get very often when people design wireless networks. They say, well, what should be the right size of my cell? And typically we say, well, if you want to design for voice or video, a good cutoff signal at the edge of the cell is about minus 65 or 67 dBm. And typically the question comes as, what is the kind of data rate I get there? And the answer typically is, well, it's complicated. So in this section, I wanted to give you a view into why is it complicated, what happens, show you a typical algorithm, Minstrel, which is a classical algorithm that can help you understand how a data rate is chosen. Your device may not be running Minstrel exactly, and I'll show you how you may want to analyze your device to understand what is its logic. But at least I hope that you will understand what is the structure of how that kind of data rate decision is made to help you design your networks better. And of course, if we look at 802.11 itself, the standard, it doesn't provide much guidance there. It does provide a little bit because at the end of each clause, there is a table that is called the receive sensitivity performance requirement. And that table says that if you are saying that you're supporting a certain modulation scheme, a certain modulation type, then you should be able to demodulate that modulation signal 90% of the time at a certain signal strength level that you see on the table for OFDM on the left side, then 11N, 11AC, and at the bottom of the right side, 11AX. So what you could say is, well, let me assume that the link is symmetric between me and the access point. So what I read from the AP is the same kind of signal the AP would be reading from me. Then let's take a margin buffer and assume that the other side is going to have this IEEE performance. And then by using that logic, I could pick up in the table, add my buffer link budget and pick up the rate. So you would think if you are receiving from the AP a probe response, for example, that is being reaching to you at minus 67 dBm, you could take a 10 dB margin and say, okay, let's assume it's 10 dB worse and 77 dBm, and pick up from the table whatever rate you think is the match for that data rate signal, and that would be 24 megabit per second. You would think that this is the way it could work. However, it doesn't work that way. And the reason why is because for any given signal level, now you have multiple choices. So if you pick up any good signal at the edge of the cell, like minus 68 dBm, for example, well, there, depending on the number of spatial streams that you want to use, depending on the channel width that you want to use, you may have a multiplicity of choices between the data rate that you could be using. So which one is the best? Well, it's not clear. Why would you choose 2 streams instead of 1? Would you pick up 80 megahertz instead of 40? Sending 1 stream instead of 2? What's the best? And also, it's not exactly sure that the link is going to be symmetrical, which means that at the AP, the conditions might be slightly different from where you are now. And that matters in 2 ways. First, you have to take that link margin, but also you cannot be sure that at minus 68, it's always the same right choice. There may be cases where now, 1 rate is not going to work. But, in 5 seconds, in the same data rate environment, same signal level, minus 68 from the AP, that rate would work. So it's something which is very dynamic. So there has been a lot of research into what is the best data rate, how it is chosen, how you move from one to the other, what happens if it doesn't work, how long do you take before you retry one, etc. And you see on the table at the bottom of the screen, all the attempts that have been made to study those algorithms. And there are probably many more than those. In this section, I wanted to show you one of them, which is the classical. It's called Minstrel. You may have heard of it if you've heard of data rates before. If you haven't, this one is very, very well known for multiple reasons. One, it's the first one that was implemented in open source in Linux back in the days of OFDM 11A and 11G. So it's something that has been published and publicized. So a lot of people have been able to study how it worked and, of course, improve upon it. And it has, undergone a lot of evolution over the advent of 11N, 11AC, etc. So it's a very good reference. Today, it's likely that your algorithm is not going to be exactly Minstrel, but it's probably something which is inherited from the research on Minstrel. So understanding Minstrel will probably allow you to understand the others. So Minstrel is something which was released back in the early 2000s as an Atheros brought up of open source implementation so that it could run on Linux. And you see the name Minstrel. If you're not a native speaker, Minstrel is that a wandering musician that is going to pick up the best contract, the best deal to try to make some money. So here the idea is to say that you would be wandering around the different rates, picking up the one that suits you most, that gives you the best bang for your buck, as we say. That is to say, the best data rate throughput for the least amounts of energy. So in that structure, you have to do a few things. You have to be able to pick up the first rate. That's the first thing. Then you have to try it out, see if it works. And if it works, you have to record that it's working and then collect statistics over a certain amount of time. And then you also have to know if there wouldn't be a better rate. And that is also true if this rate doesn't work. You have to be able to pick up another one. So there must be a sort of rate ranking structure where you decide which rate is good, which one is bad. And that thing needs to be refreshed, not in real time, but close to real time. And then, of course, you have to have a plan, which means that if you use a rate which you think is best and it doesn't work, then you have to have a plan B, a plan C. How do you switch off to another rate so that you can empty your buffer with something that is going to be working seamlessly. So that means it's sort of a virtuous circle where you have some testing, election of a rate, statistical collection of what happens, and then testing again, and then referring the rate that's been working for you in the past, forgetting some things that were long ago, remembering what's been recent. So there is a sort of a structure in the way you're going to be collecting information about those different rates. So it's a little bit of a long range process. So let me show you how it works. But first of all, you have to pick up a first rate. So here, because Minstrel is an open source and because it's been implemented in various ways over the years with the HT, VHT, and what we call RTS, which is the latest one, there are a few different approaches there. But let's take it simple. The first thing you want to do is to understand what rates are available to you. So what you would do here is to take all the rates your card supports, right? And then organize them in bins, in groups. So for example, you say all the first one stream rates together, all the two streams rates together, etc. And then you organize based on channel width. So you create buckets of rates that have the same characteristics. And this is useful for you because when you talk to an access point, and of course you could also talk to another station in peer-to-peer mode, you're going to exchange with that station initial discovery messages where you're going to have capabilities exchange, where you know what the other side is going to be supporting. So the first thing you do is you organize those buckets, and then of course you wipe out all the buckets that match things that the other side cannot do. If the other side cannot do 80 megahertz, all those go to the bin for that communication. Of course, it may be usable for others. If the other side doesn't do 4 streams, all right, you done those. Okay, then what you could do from that first list is to organize the rates into those that are supported, and then look at the signal from the AP. I said this is optional because although I'm going to assume that you're doing that for now, just for the sake of getting us up to speed, it is not entirely necessary. Some structures, implementations ignore that completely. But to make it approachable, let's suppose you do that, as we were saying in the previous slide. You're going to look at the signal from the AP, then you have all these rates that the AP supports, and then what you're going to do is, for that level of signal, you're going to pick the rates in these different buckets that can work. And that somehow goes back to our table from 802.11 with your link budget, etc., except that, of course, you trimmed off all the rates that the other side didn't do. And then what you're going to do is to compute for each of those possible rates the one that is going to allow you to transmit a certain amount of bytes in the minimum amount of time. So this is not something which is entirely obvious, right? Because if you send over 80 megahertz, 40 megahertz, or 1 stream, 2 streams, 4 streams, etc., each time you will have to create some overhead into the header. Your preamble will be the same. So the structure is going to pick up the frame that you plan on sending next. And that frame will have a certain number of data bytes. And you're going to compute for each of those rates available to you now, which of those is going to be able to transmit this amount of bytes in the smallest amount of time. And that, of course, will be a combination of how many streams and the modulation you choose. And then you pick up that rate. So that is just to get you started, because the conditions are going to change all the time. So now you have something that allows you to send one packet, but what about the next ones? Well, you would keep in mind that things are changing all the time. And because they are, what you want to do too is to be able to sort the rates that are available to you, to dynamically be able to pick up a better rate if there is one, and if things go wrong, rate shift down to something. So what Minstrel does is typically slice the time into 100 millisecond windows. Again, that could be implemented in a different type of structure, but that gives you a sort of a time window where you're going to think. And then we say, we're going to alternate what we call non-sampling, which I would call efficiency windows, where you want to empty your buffer as fast as possible. And then sampling windows, that is to say times where you say, my buffer is not too full, so I'm okay to experiment a little bit with different rates. So we're going to alternate these sampling and non-sampling windows. And then during the sampling windows, what you're going to do is to, out of all these buckets available to you, that works with the access points, you're going to pick up randomly a rate in any of those buckets. And then you're going to try it out. And you're going to see if it's going to give you efficiency, if you can send something with that. If it fails, you're going to retry a certain number of time, which initially maybe statically set to a certain number, say 3 attempts, and then you try something else. But as you'll see in the upcoming slides, as you get better at understanding your rates, you will have a retry which is going to be dependent on how good that rate might be for your next transmission. So then what you're going to do is, for each of those random rates, you're going to establish a sort of success rate that they call throughput. But throughput is not only understood as just how much bytes you can send per second. It's more than that. It is that, but it's not understanding based on the modulation. It's also looking at what we'll see next slide, which is how many frames do you lose when you try that rate? How many successful frames you have? How many are going to be failing? And this is important because you have to keep in mind that it's not because one attempt fails that the rate itself doesn't work. It may be that you have a collision, then you have one retry, so that rate kind of worked, but you don't know if the first attempt failed because of a collision, or if you are just borderline, at the edge of what can be done with that access point where you are, and if it's just RF conditions that make that the noise figure increase a little bit at the AP, preventing it from demodulating the first attempt, but it could demodulate the second one. So you want to remember each failure, and that is going to affect the throughput you can get from that rate, because essentially sometimes that rate doesn't work. And of course, you may have collision ones, but statistically speaking, as you keep trying that rate, you will have understanding of how often that rate is typically working compared to the others. So that's going to kind of remove out the collision, because the collision is likely to be about the same throughout the life of your connection at the scale of these few hundred milliseconds compared to the other. So you are going to be able to understand how that rate works compared to the other, all rates having the same kind of collision rate, but the noise figure is going to be different depending on how good the signal is. So what you're going to do then is to organize in those buckets those rates, try them out at random interval. And I say random on quote here, you see on the slide, because you'll see it's not entirely random, but it's Minstrel, right? So you're wandering around those different rates. And then you're going to classify those rates based on how good they are, what performances they give you. And in the end of that sampling period, what you want to retain is not, a full list. Of course, you retain a full list, but primarily what you want to dump in the short memory of your car driver is 3 rates. The best one, that is the one that has the highest success rate and gives you the highest throughput. At the same time, a second top two, second rate, and then the 1B rate that you try that has the highest success rate. So this is likely to be something more robust, but something that works all the time. So you know that when you'll be moving out of the sampling period into the non-sampling period, the efficiency period, you'll be able to use that top rate, which is the most optimal for now, for the next 100 milliseconds. If that one starts failing, you can retry a certain number of times, and we'll see how in a few slides. And if that one fails, you can switch to the second best. And if that one fails as well, you can switch to the top one, which is the top successful one, which is maybe much slower, but this one seems to be working always. So it allows you to empty your buffer and finish that non-sampling efficiency window before retrying the new conditions and attempting new rates. Okay, so let's look into this idea of a throughput. I said it was a bit complicated. It is. We're not just looking at the amount of bytes per second in the rate here. We are also incorporating 2 things. One is what we call the FLR, which is the frame loss rate. And that's fairly obvious. If you attempt 3 times and then there is 1 failure and 2 successes, your success rate is 2/3, 66%, right? That's very obvious. So you want to remember that success rate, because again, if you're at the edge of that signal level, you want to know that this rate is like sometimes failing because you're just at the edge of what can be done at the signal level where you are. But also, conditions are changing. So Minstrel also incorporates something that we call UNA, which is exponential weighted moving average, as you see at the bottom. And this is an equation that looks a little bit complicated. I'll show you how it works in an example in the next slide. But essentially what it does, it says, I'm going to define a lambda value, which is the weight factor. And that's the weight of your memory, how much you want to remember from the past. And then what you're going to do is to look at the success rate, the FLR of your current transmission. For example, in the slide, you see 0.8, that it means 80% of the frames you send at that rate are successful. And then you're going to incorporate how much the frames were successful in the previous sampling periods you tried in the past for that same rate. And as you go beyond the past, you see the equation goes 1 minus that lambda value times the FLR value. And then that's for the previous window, test window. And then 2 windows ago, you're going to square that value. And then 3 windows ago, cube the value, etc. So what does that mean? Well, let's take an example. Suppose that you have now a transmission rate, and let's start on the left side. That is fairly bad now. So you have this lambda which shows, and again, it's arbitrary. You could change it as open source, but let's take something like 0.8, which is fairly important. I want to remember the past. And then today, right now, in the sampling window, your success rate is pretty poor. It's 10%. So that's pretty bad. So you say, well, that's probably not a good rate. However, in the previous sampling window, the success rate was about 40%. So that was half-half, not great, but still better than 10%. And in the previous window, it was 80%. So super good, right? 80% success. So by combining those together, you're going to combine them to create this throughput quote value, which is in fact a score. And what that gives is what you see on the left side, where we say you're going to do this lambda times the success rate now, 0.1, 10%, plus 1 minus that lambda times the previous window score, 0.4, plus 1 minus 0.8, that lambda thing, times the previous score, 0.8, but this time squared. And then you could go on, 3 windows ago and so on. You can continue that for a certain number of windows you want to remember. And you see that the output here is that your throughput value is not 0.10, it's 0.28. And that what that says that, okay, my rate is not good now, but it's not bad as a rate because it used to work. So maybe conditions are changing. So I want to have a good emphasis on the fact that now it's not working, but because I chose a lambda fairly high, I want to have a good memory that it used to work. And that means that although this rate is not great now, I don't want to push it down to the bottom of my queue saying, well, ooh, that's ugly rate, I don't want to use it. You want to remember this rate used to be good. So you want to keep it a little bit higher in your stack saying, well, maybe it's going to work again because maybe what I'm experiencing now is very temporary. There is some noise on the AP or something. Taking another example on the right side, suppose it's the other way around. Now your success rate is super good, 80%. It was kind of in one sampling window ago, 40%, and even worse, before 10%. When you do the same math with that kind of structure, you see that now your score, your UNAS score is 0.72. So it's the same thing, right? You're saying it's 80% success now. I don't want to assume, that is exactly my rate I want to remember because it used to be bad before. So although it's good now, maybe it's because I'm in a particular good spot and maybe it's going to be changing and getting back worse again. So I don't want to keep the value as high as it is now. I want to remember what happened in the past. So in other words, that structure allows you to test the success rate of each rate, but also give a sort of a memory value to the past. And of course, the farther away you go in the past, because you're squaring, cubing, etc., numbers which are between 0 and 1, they get smaller and smaller as you do that, you're going to put less and less importance into the past as the past go farther and farther away. So that's the logic of this UNA. Okay, then that will give you an idea of what rates are good, what rates are bad with this UNA score. So what you're going to do next is to combine that UNA score with this performance that we're describing in the initial choice of your rate, where you say, for that data rate, if I'm using that data rate, how many bytes can I send? How long does it take for me to send a certain number of bytes? And you're going to pick up also ranking based not only on the success of that rate, but also on the throughput of that rate, the amount of bytes you can send per unit of time, on that rate. So you're going to combine those two together because the rate is reliable 100%, then of course, its weight is exactly the same as its performance in terms of how many bytes it can send per unit of time. But of course, if you fail sometimes, this is going to weigh down the efficiency of that link to give you how many bytes you can send for real, because some of them are going to be just retries. So the throughput score you'll get in the end will be a combination of these two. How many bytes you can send in theory times, how really this UNA score weights down the success rates of that. And then in your bucket, you're going to put up those that have a better score, a better throughput score. Why this is important? Because when we say that you're going to pick up scores, rates at random during the sampling window, it is not entirely true anymore. It used to be true in the early days of Minstrel, but picking up at random scores that are not going to be working well, that is not very clever. So what Minstrel did then as an improvement is to affect a statistical preference for rates that have a better score. So when you get the sampling window, you're not going to only test all the rates that you can within that sampling window. You're also going to test more often the rates that are likely to be better, the ones that have a better score. Because you just don't want to set up a list. You want to pick up the top rates that you can for the next transmission window. And of course, as you're sampling in that window, you're also transmitting data. So you want to increase your chance of being successful in that transmission. So the algorithm itself puts a preference to try rates that we know have been successful in the past, those that have a higher rate. So you're going to pick up those and try all of those during the sampling window. You'll try all the rates, but you'll try those that are successful much more. Okay, so now that we have this logic, we know which rates are top rates. And as the time will go by, we'll re-enter these windows, and then we'll be able to reorganize, resort our rates based on their success rate as the time goes by, and we'll re-actualize this list. Now, when we have failures, we need to do something, right? And as we said before, what you're going to do is to pick the top rate, try it, and if it fails a certain number of times, you're going to pick the second rate. And if this one fails a certain number of time, you're going to pick up the strongest rate, the one that is probably the highest successful, even if it's much slower, so that you can finish this non-sampling window, empty your buffer until you retry again. But how many times do you retry? Well, here again, it is not entirely fixed. There is a trial value which is statically set as a beginning value, and we set typically 3, for example. But then what Minstrel does is to say it is not a certain number of time that you want to care about. It's a time it takes you to retry your frames. So what Minstrel does is to set up a sort of a retry time window. we say if you try something, it fails, I will allow you to continue trying for a certain number of milliseconds. And you see typically it's 79.2. It used to be smaller, by the way. It used to be 24 in the times of BG. So what that does is that it says, then based on your UNAS score, I'm going to allow you to try within that window a certain percentage of that window. In other words, if your score is perfect, then it should be working. So I'm going to let you try. If it fails, I'm going to let you retry again. And you may be trying like 30 times plus. Here in a classical transmission, you can retry 33 times at 54 megs, for example. So depending on what is the data rate, the MCS you're using, the retry is going to take a certain amount of time. And you keep trying until you exhaust that percentage window allowed for you for this retry for that rate within that max window of 79.2. If your UNAS score is very poor, like it fails most of the time, and you happen to be using that rate, you're going to try once, and then you may be allowing to try a second time, but then you say, let's get off that rate. It's not working often anyway. So you see the amount of retries you're going to have at a certain rate is not fixed. It's going to be dependent on how successful this score, this data rate is likely to be. And based on that likely successfulness, you'll be allowing a certain time window. And within that time window, how many times you retry? Well, that depends very much on what speed that data rate allows you to transmit at. Maybe it's a 5 retries, maybe 30 retries, depending on how many bytes you can try within this. So you're going to record that retry rate as a consequence of your throughput score for each of the rates. And then of course as you'll be picking up this top score, you'll try that certain number of time that matches the retry value for that top score. If you fail, you go to the second top. If you fail, you go to the robust one. And that's how you proceed. So in summary, the way you're going to do Minstrel is very much dependent on how you're going to be testing the environment. There may be some initial values, and I said, it's optional to look at the rate, and very often it doesn't even look at the rate. It just starts randomly in that sampling window and starts from there, because in the sampling window, you're going to be trying all the rates anyway. So it just starts from there, and it initiates the initial values for this UNAS score, for the throughput score, for this retry rate, and then start from there. And then as you keep trying every 100 millisecond window, you try to empty your buffer, being efficient, and then you re-enter a test window of 100 milliseconds, and you keep on going every time. At the end of each sampling window, you're going to reorganize which rate is the top rate for the next non-sampling performance window, which one is the second, which one is the more robust, and then you continue from there. So is your device running Minstrel? Probably not, because Minstrel, again, is a very, very classical structure, but it's been evolving over the years, and many algorithms have been trying to improve on Minstrel in a few different ways. But logic, is often the same. For example, Mira is a MIMO, you see the term at the bottom, right? MIMO, where rate adaptation takes Minstrel, but say, I want to focus on the idea that you should be able to do multiple user, MIMO, multiple input, multiple outputs, which means that I'm going to do Minstrel, but with a MIMO focus. And also this idea of trying all rates doesn't make sense, because most of the time you want to send fast. So what Mira does is says, instead of trying all the rates, but in preference the best ones, try to have a sort of a zigzag logic where you try to try more the efficient rates, but trying to convert your way into a rate which is more efficient. So you try low, try high. If it fails, you go down. And if it's successful, you go back a little bit up, and then you try to zigzag your way into the optimal rate instead of trying at random. Another one, which is called RAMAS, Rapid Adaptation for Multiple Antenna System, is also working on the logic where you say, instead of having these buckets, why don't we have what we call the data rates, and then what we call enhancements groups, like special streams, width of the channel, etc. And then in the very banking system, I'm going to check my rates like Minstrel, but then also have a sort of a credit that is given by the ability to have those options to expand the channel or to expand the number of special streams. And depending on the attempts you make a la Minstrel still, but you will have this core rate to which you'll be able to stick on some credit to allow you to expand beyond the pure rate in 20 megahertz one stream to get to 40, to 80, to streams, etc. There's also the Dionysus. You may know that's the giant in the Greek mythology. What it does here is to say, well, I'm going to use Minstrel, but I want also to look at the coloring scheme in 11AX, where the OBS SPD, when you want to dynamically change the power, because so far we haven't been talking about power. So what it does is that it does a sort of sorting like Minstrel, but it also looks at the OBS SPD threshold for each of the time windows, and also what is the current power of the station, and it dynamically adapts, not only the data rate, but also the power of the station depending on those conditions. So, those are a few examples. I'll give you in 2 slides a reading list if you're interested to reading more. But what that tells me is that your system may be running something like Minstrel, or maybe something slightly different. It's likely to be an implementation that will depend on the environment. For example, you see here 2 examples, one with an iPhone and another one with a Samsung Galaxy, and at the bottom, a cheap Android. The way you capture that, you can use Wireshark, for example, and then you look at the data rates transmission from that station. Maybe, initially as you start the station if you want, and then if you can, try to move the station right behind a big obstacle like a piece of metal or something, and look like how it goes downhill. In terms of data rates, and then you remove the obstacle, and then you look at how it's going to rate shift up. So you see here, the iPhone is using a Myra, and Samsung Galaxy as well, where it's going to try to bring its way up, but it's an enhanced Myra where it's also remembering not only the top 2, but the top end. So it's a sorting system. So you're going to climb your way up to the top rates. Here we are obviously outside of the sampling window. In the sampling window, you would see some more zigzag, although the signal would be the same. So if you want to test yours, what you could do is to run those tests, run this capture and see what happens. But please be aware that your algorithm is going to be depending on many things, and that's why I keep saying it's complicated. One, it's going to be dependence on chipset vendor. Each vendor has their own implementation, which is typically derived from Minstrel, but implemented with some internal sauce that they keep improving from one generation to the other. So it's a Minstrel plus system. But also device type, something which is intended for enterprise environments. They will be expecting a lot of changes and a lot of movement, people on calls with Zoom or something else. So they will be very aggressive in the way they resample very often. Whereas if it's a home environment, you want to go into a steady state that is going to be more stable. So you want something less aggressive, more battery efficient, but also more jumpy in its choice. So it's going to be very much dependent on the line of product you have. Also, it's very commonly depending on the hardware, but also on the software, the firmware on that. So what you can expect is that for each and every single phone you have, tablet you have, the type of adaptation algorithm you have will likely change from one version of the OS to the next one, as they keep refining to take into account new APs that come up with the MNAX. So you want to be slightly different in the aggressivity, repositioning of the product on the market, etc. There may be some differences in the way you want to attack those adaptation algorithm, and also based on statistics coming from their customers, they want to improve these things always. So it's complicated, but if you want to test, you can, and I will give you for that version of software you have what kind of structure you will see. If you're interested in reading more about how this works, these 2 papers are very good. They will give you an overview of the others, more in detail, of course, in Minstrel, Myra, Adamesos, and the others, but it will also give you a view of the set of research, and they're fairly recent, into those algorithms. So we'll have a long list of all these algorithms, and you'll see the different structure. And you'll see that different algorithms have different approaches. So that will also give you an idea into what is the engineering logic behind it. All right, so let me pause here, and if we have time for live question, let's go to live questions.
Here we are again with Jerome Henry. Jerome, thank you for joining us again. And we're going to be talking about one of the questions that came in related to your presentation. But thank you very much for that presentation. It's one of the best I've seen on the topic, and we really appreciate you providing that here.
Thank you. I'm super happy it's useful. I'm looking at the people's feedback. I'm super grateful that people like it and find it useful.
Excellent. And in addition, one of the questions that came in was about the slides, and you have graciously volunteered to provide those to us. We'll be making them available in the description here, so they'll be available here as long as excelevents.com keeps this open, which will be for 30 days after the conference. So you can come out here and get them in PDF format by just coming back to this particular talk, looking at the description, and you'll see the link there within the next week or so. So we'll make those available to you. And then, Jerome, we did have another question that came in as well. Jim asks, could these algorithms be simplified if vendors implemented MCS feedback, aka link adaptation? What do you think?
Yeah, in theory, it could. The major issue is that the SNR is difficult to evaluate, which means that we can feedback on the MCSs we're using, on the RSSI, but the SNR is very local, and it's changing very fast. Within 100 milliseconds, you may be moving around, and that would be changing the deal all the time. So the feedback mechanism would be fairly heavy to implement. And that's why most vendors have said, let's just do our logic here, how we see the world, and use that information to decide how we should be sending, instead of having this exchange, which would be too complicated.
Gotcha. Okay, well, we just had a short time. Thanks for coming in live with us again today. And on behalf of everybody in the wireless community, let me just say thanks for all the training you've done over the years, because it's been some really good e-learning, some of the best clear instruction that's out there. So thank you very much for all you do and for being with us today.
Well, thank you, Tom. Thank you for driving this effort. And thank you guys for organizing all this together and sticking to this event. It was a great event. Thank you.
Excellent. Thanks, Jerome. Take care.
You too.